other process phenomena, control is a dynamic process because you have to take decisions in seconds, minutes, whatsoever. Where what else? Whatever else we have learned is mostly steady state or spatially varying. I'll say spatially distributed. For instance, if you look at a reactor, you might be interested to draw a flow profile spatially, be it plug flow or even whatsoever. You would like to draw the how the velocity profile changes, concentration profile changes, mostly spatially. But here we are interested in more spatially, okay, and temporally. The spatial thing is of not that great importance and could be approximated because your temporal variations are so huge, so that the spatial variation could be approximated. So we are mostly looking at temporal variations of the process. So we have learned the dynamical model. Okay, unfortunately, all of these models happen to be ODEs or PDEs. PDE comes in when you have this spatial and temporal. ODE is mostly temporal. So that's why S and T, but this is T alone. Okay, then what we did, and other issue we might see is things are all nonlinear. Because none of our chemical process, see, you might be surprised to hear that many of the applications such as robotics, their models are still linear compared to chemical engineering. That's why you would see the automation. Of course, there are other different challenges while doing automation of robotics, etc., but not in terms of the process characteristics. First of all, your so see this process control and automation is very generic. It has applications in chemical engineering, mechanical engineering, electrical engineering, and it's all interface, this cutting like emerging fields like robotics. So we are not alone in this world dealing with this problem. But the unique problem that chemical engineers face is this all these things. Things are spatial and temporal variable, and things are non-linear. Mechanical also some systems, but see most of their systems in mechanical, for instance, spring mass damper. So this is their classic problem. So they are not as complex as chemical engineering process because of this reaction. So this is a key what you call game changer in our overall scheme of analysis. So reaction, energy exchange. So these two are making things tremendously nonlinear because if you look at any reaction and model you see in a linear stem, or if you look at more complex, you would see much more complexity. Energy exchange. MCP delta T is okay, but if you have any other more complex energy exchange terms, things tend to be nonlinear. And also spatially and temporally variable because you could radiate, the heat exchange could be radially varying and temporally varying. So this is what this problem is slightly unique compared to these four. It's all clean, but we are it would be a little difficult for them to digest. You will have to explain why this is because everybody would think their domain is of the most difficult domain to do. Because I do have some experience in working with all of these domains, I can confidently say that chemical engineering control problems are the toughest. Okay. Okay. So other typical or maybe very unusual thing that you would really see in chemical engineering problem is the time delay. So if you, for instance, if you are playing with a robot, if you give an instruction, it would execute immediately. Because see the ambit in which they would all play around is very small. But chemical engineering, no, there are n number of things. We'll come to that. Because the controller is sitting somewhere. See, I am not denying the fact that there may be some delay in execution of some of the actions by a robot. But that may be in fractions of seconds or even in seconds. Here it may be in minutes or even very slow, maybe a couple of minutes, 10, 15 minutes. So time delay is a big problem. Okay, so now these are the what you call additional ingredients that makes our problem complex. Then again, we'll have to deal with this in various ways. One is linearization, so that to some extent non-linearity can be avoided. ODE, dealt can be dealt with Laplace, so that something can be got away with. So these would give you models. So now we are good to look at how the dynamics are varying. So here your dynamics join. You would see when till, so this is what our three minor topics possibly we have done. And so in fact not three minor, we also talked about a little bit of data driven model. So this is the machine learning sphere. Okay, so now you see how this is very nicely connecting over here. So moving further ahead. So now you have to do control. That was the second part. So for control we started. So we had the lacuna of modeling and we learned how to model. Then we have looked at controllers. So the three important aspects of control, types of control. In fact, there are many. Maybe I can list. This is what you have learned maybe in the last couple of days. P, PI, PID. So these are very basic. So if you talk about PID controller to an advanced control thing, they'll say that they are all. But they are nonetheless they are basic, but they are the fundamental blocks. So because the advantage of unlike any complex controllers, these could be embedded in circuits, embedded as electronic circuits. So which essentially means that you have a hardware version to this. Of course, you will have a software version, but you will have a hardware version also. So that's a big thing, right? So if you wanted to make any circuit, okay, and or let's say you don't have a, so how do you do this? Basically, what is a control? So you have just learned the controller. What is a controller? Controller just do a, it's a rule, technically speaking. It takes up error and suggests what to do to its next customer. So who is the next customer? Typically a final control element or control valve. It would take up the error, okay, do some conversion. Typically means of a rule. So what does the rule? This rule would essentially try to reduce the error. So this rule, all this, either of these rules are belonging to either of these categories, PI and PID. Okay, and you have this is our analog. See, whatever you have learned till now is in terms of the transfer function, so Laplace form of this. We will now quickly see it digital. Maybe so that is what we are going to get started up for today. Digital version in the sense that they are not. This is continuous time. Laplace is continuous time, but digital is discrete time. So it's a fundamental difference, right? Digital and analog. Is discrete in sphere. So, okay, so we would do this now. Then we will move into what we known as the overall control system design. Okay, so this is going to be our new topic, which we would now look. What do you mean by overall control system design? Till now we were looking, okay, model, Okay, controller, control valve, maybe sensor, etc. In isolation, we were looking them independently because we are trying to get the ingredient fixed first, right? So first of all, you have to prepare your ingredient, then you go and make your recipe. So we till now we were trying to fix our ingredient. Okay. So now we will look them as a whole. So if your overall control system would contain everything, it would contain a model. It's essentially your plant itself. Controller, control valve, sensor, huh? And what else I'm missing? So people also call this I to P, which is current to pressure transducer, because you need control valve, you need air supply, and how the system behaves as a whole. This is going to be our next step. Okay, once that is done, okay. So the next important thing. So see, we have seen PI and PI and PI and PID, and we also have learned about three parameters: KC, tau I, and tau D. They are controller parameters. And we know what qualitatively how they are, what their implications. For instance, if Kc increases to infinity, you will have reduced offset. Tau I is much more smaller, oscillations are more. Tau D is, so we know qualitatively how these affects the overall performance. So now, but once you design, so see, I consider this as a design problem. You are going to do this in the field. So in fact, this is the exact same thing that you would go and do if you are given with a design assignment. So once you fix the overall control system design, okay, so now the next is tuning the controller. Okay, what do you mean by tuning the controller? Fixing the optimal value of Kc, tau I, and D. Fixing your Kc, tau I, and tau D. This is again, so we are limiting our discussions to only P, PI, and PID controller, and also maybe on off to some extent. So on off is a special category of P controller. So why we are saying that? So what is the P controller profile? You would have seen it would be either of this form, or it would be either of, okay, or it could be it's both. So this is P. And on-off controller means that it operates either on or off. On, if this is on, this is off. Or if this is on, this is off, whatsoever. Which essentially means that this line, right? This line slope has been moved over here. So this is the operating sphere of on-off. Okay, this is the operating sphere of P. So basically, what are you doing? You are shifting this line to this, basically making slope kind of infinity to some extent. So that's what. No, so it hits the y-axis. You are making this what you call slope of the P controller line moving towards and making it to the it touch the y-axis. Then it become on-off control because it has two states, either on or off. So P controller is a special category. Sorry, on-off is a, you may assume that on-off is a special category control, but that is also widely used. Okay, heater, non-inverter, AC. Maybe to some extent. So you have seen this. This is like a widely used control strategy, which is part of our day-to-day life, which we don't kind of realize that. Okay, so now as I told, so once you are designed the controller, you would go and tune this. So this is going to be the next new topic. So this is maybe less. So this is, I would say, T1 that we are going to cover. This would be T2 that we are going to cover. And the last is a very different perspective of looking at the control system, which is known as frequency response. Frequency response and controller design. Okay, so this is going to be the new topic E3, I will say, and I would assume by that time our semester would come to an end. Okay, if you have time, we will see something more we could do, but these are the three topics that we would fundamentally focus on, so that you are now from end to end. So this overall scheme is something that you should carry in your neurons, so that eventually you should be able to relate everything. So what is frequency response? Couple of I'll spoke about a few one or two lines, then we'll go back and start looking at our problem. See, as you really see here, right? So everything is signal. Be it a measurement signal, be it a process signal, controller out, everything is signal. See the other people. So see, we have listed down some people, no? So these are cross-disciplinary guys who kind of trying to understand this problem together. Chemical engineers, mechanical engineers, electrical engineers. See, electrical engineers also there are few people who do communication. In fact, sometimes it is fully communication also. So when some of the communication people started looking at the problem, okay, they found that okay, so this is okay. Basically, what you are doing is just like what you call an elephant. I don't know, it's a good elephant though. Okay, let's seeing by very so chemical engineers seeing it, mechanical engineers seeing it, electrical engineers seeing it, and finally communication people started looking at it. So they what they have seen, okay. So this is all signals. Could you say something else? It's all signals. Signal processing is our domain. So uh, let's have a what you call our version to it. So if you start looking everything as a signal, okay, because it's all signal, no? Temperature profile, it's a signal. It's a profile, but it's a signal, no? So you're measuring something, so you're getting something. Controller output, it's a signal. So typically, the domain of electronics people, so communication basically, they are looked the signal from a very different angle, no? So which is generally known as frequency of the signal, which is the dominant frequency, which is the non-dominant frequency. And you should be able to kind of give interpretation based on frequency also. But here we are all based on the time domain. So till now, so there are two classes of people. So we were only looking at time domain. Because everything that we write will have a function of t or a function of f, while t and f can be interchangeable. You can move from t to s and s to t. So they are all time domain, or maybe Laplace domain. I would again like to call it as time domain because it is just a conversion. And you would have discrete time here. This time could be discrete or continuous. So when the other people jumped into the game and they started looking this problem as a signal, they say that okay, this is not only time. So see, there are three different information coming: time, okay, I'll say frequency, and Laplace. Laplace and time, I'll say like this, like this. This was the original understanding that we had. So what time domain people do is, okay, there is some ongoing connection between Laplace and frequency because S, Laplace function S, could be replaced as j omega, where j omega is j is your what you call complex number, and omega is the frequency. We'll see that is what when we look at the frequency response is what we are going to see. So there is some ongoing connection between Laplace and frequency. So when what you call this the notion of signal coming into the picture, then we are going to kind of close the loop. So we can move from time to frequency, frequency to Laplace, Laplace to frequency. This all obtained by means of virtue of looking at the problem from different aspects. So we are good at looking at possibly time domain, chemical engineers, and Laplace may be mostly brought by electrical engineers, and frequency mostly brought by electronics people who do communication. But that's the beauty of this problem. No? So this could be, you could solve this problem from any angle. If you could solve it from the time domain perspective, then you will have to always deal with the ODE, which is difficult. So but then you hired Laplace and moved and tried to solve the problem there. And again, so now this other enrichment came in, this frequency. So we will not go into the detail, but we will look at the pointers of frequency response perspective of controller design. And I think by that time we would mostly towards, so when is the exam, Ashutosh? I think when is the last day of class? November, I think. So 15, I know the exam starts.
Sir, it's 12th November.
12th November is the last working day. And we are, today is I think 13th November, October, no? So we are
Yes, sir.
exactly 1 month. Which, let's assume that we could cover the all of this. So today's, after today's class, this week you are going to have a long vacation till next Wednesday. So the tentative plan is by this week and next week we will cover. So 2 weeks. Oh, I'm sorry. Okay. Time it behaves. Okay, so now the tentative plan would be, this would be in the coming 2 weeks, it would most likely take. Okay, now each of the topics, 1 week, 1 week. So 4 weeks is like a bang on. So even if you have 4 weeks, we will cover T1, T2, T3, and the remaining time would be spent for discussions and problem solving. So this is the overall picture that I am planning. But if we could not cover T2, T3, T1, T2, T3, I will post some videos because all these things have to be covered. So I would expect that we will have enough time. But by any means we could not at least cover one of this. I would at least post some clip lecture so that this end to end is given as a package to you. So any feedback on this? Everyone, anyone? Are you all there?
So I would need to discuss with the class once and probably can let you know the feedback if there's any.
Good, perfect. So I hope you got the feeling, right? So this is what we are going to have. So T1 we will start. T2 would be, so this week and next week would be the topic 1, which is basically the control system design. Okay, then T2 would be your tuning, and the last would be your frequency response. And I am okay to open up any of the what you call off slots of, or like unused tutorial slots for discussions and problem solving if you need to. But yeah, so you should tell me. I am always available. So this is the way we are going to do it. So now let's coming back. So I was trying to give you an overview so that you don't see whenever you, so most of the problem that most of us, when we start looking at the problem in a macro level, we would forget about what is that which part of this we are going to learn. So that's why I was trying to give you an overall perspective so that you don't miss, and you should not feel what is this like. So you should always be able to appreciate each and everything. Give me a minute now. Yeah. Okay, so the pending topic from the controller part is what we are going to cover in maybe in another 5-10 minutes. It's very quite simple, nothing else. It is the digital version of the PID. So till that time we have all learned about transfer function form of PID. 1 by tau IS plus tau D. So this is the transfer function, which is essentially means that it is in the Laplace domain, or again, as I told, continuous time domain. Now, with that, so see, as I told, you would either implement this as an electronic circuit, or you can do it by, so because this is a rule, right? You take an error, do a transformation, and give you an output. So, so as I told, this is a rule. So when we talk about, so the other way to do it in terms of this is electronic circuit. The other way is to do it by means of hardware, which is by means of distributed control system, which is kept somewhere in a corner of a plant, where you take out the signal, do this conversion, do the algorithmic transformation, and find out the output and send it back. So of course, computer know only bits and bytes, right? So you doesn't know what is a continuous signal. So that's very important. You see, whatever we have learned, when you bring in this big guy, which is supposed to help us, it's also making our life little difficult because it doesn't understand what is continuous time. It will always work with discrete time. Because so what computer can only know, it's always work in bits, right? So you cannot do any continuous transformation. The simplest form is to convert all of them into discrete time. So that, so of course, eventuality, which essentially means that, so that's what I am trying to say. We thought DCS would help us. Of course, it is helping us to do this transformation without the help of a circuit. But the pay, so technically, so this is something that I would always speak. There is no free lunch. In the world, there is no free lunch. Something of the other is compromised anywhere or everywhere. So when you move from continuous time to discrete time, then the law that you're going is you're discretizing. So what discretization means that error. So for instance, the integral error. So integral error is what? Integration of error over time. The discrete time equivalent is what? Summation of the error over some certain time interval. This is discrete and this is continuous time. This is discrete time. Similarly, the other term. So there are three terms in the what you call your PID controllers. So this is evaluated at a particular time, E of t, while this is the integral term and while this is the derivative term. So the problem comes in the integral term and the derivative term, because this is of course is evaluated instantaneously and behave like a discrete term, discrete signal. So the key impediment that you need to face when you move from continuous time to discrete time is the approximation of your integral part of the controller and the derivative part of the controller. And this is also kind of badly hit us, because if you see, so the so P was functionally was the simplest controller, and that had a lot of lacuna. When you move from P to Pi, okay, what have we gained upon is the integral controller's property to eliminate the offset. And what are we now? And of course, and also the derivative times property of anticipatory control or rate of change information in the controller design. And now move back to your discrete time. You are all approximating these guys. So there is some, so which essentially means that some of the good things that you might gain tend to lose off until you don't keep your step size correct. And what is the pay again? So there is also no free lunch. If you make the step size smaller, you have to solve it for larger time span. So I hope you have underwent a numerical course, right? So for instance, numerical methods. So in the numerical methods, what is happening? So let's say if your time is between 0 and 1 and 2. So this is the discrete time integers, and continuous time means it is fully this is fully what we call filled in. Okay, so how to make it discretized? You figure out the points here. For instance, 1, 2, 3, 4. So this essentially means that each of the step size is worth 0.25, 0.5, 0.75, and 1. Okay, and what are we lost? The information in these missing regimes. Let me put a different color if needed. If this is lost, this is lost. You only know the intermediate. And this, and what is another problem? Let's say I told you cannot, and you know this. I'm just repeating it for just to make my argument complete. And of course, there is a getaway to it, which is, so see the step size. So delta t here is the step size. You might have heard h. This is the typical notion of in numerical methods where they use this word letter h to generally denote the step size whatsoever. Okay, so now coming back, the loss that you get, so you could reduce it by means of discretizing it in a very, very smaller time steps, or even the space 0, 1. So now you see, so every discrete time step is coming with one evaluation of your model. So which essentially means that if you are discretizing into 4 steps, you have to evaluate the model 4 times. That adds up to computation. Okay. And when you discretize in much more smaller step, but the problem here is that more loss of information. And if you need less loss, you discretize in finer grid. And let's say this is 10. So you are evaluating it 10 times 10 evaluation. So what have you gained? You gained the accuracy, but lost time. But here you lost accuracy, but gained time. So that's what again. So this no free lunch theorem is like classic in when you talk about optimization and control. I think this may be true for any other area, but of course this is like ubiquitous. You cannot avoid this problem. You will have to do some level of trade-off. Okay, so now if you discretize it, what your controller can have two different forms. Okay. So first of all is typically called as the position form of controller. So what does position form mean? So position form means that uh, it is just the discretized version. Okay, pk, which because now we are evaluating at a particular time instant, pk is equal to, just a second, you don't have permission to. Yeah. So it is the simplified. The position form essentially means that it is the exact discrete time version of the continuous time model. So you see, KC, EK. So this is evaluate the controller output at kth instant. Kth instant. So this k could be 1, 2, 3, 4, and this rule, this controller algorithm. So see, rule algorithm. You would see all of this term when you learn more about advanced process control and whatever. Sorry. So this particular algorithm or rule is exact discrete time formation. So your integral time is approximated and discrete time is approximated. Okay, so now you can also write it as k minus 1 instant. Okay, so then k becomes, so wherever k comes in, you substitute k minus 1. This would be k minus 1. You integrate only to k minus 1, e k minus 1, and e k minus 2. So this equation 29 is the position form. see, you can implement the digital version of the controller in two ways. One is, of course, what is known as either equation 9 or 29 or 30, which is the position form. And the second is a very interesting term. It is called velocity form. So what does velocity form mean? So look at the controller structure. So in the velocity form, what are we doing is you have the position form of two subsequent times and you subtract them together. 29 minus 30. So this is the position form at the kth instance. This is the other one is the position form at the k minus in one instance. Okay. And what is called the velocity form or the velocity form of the velocity form digital version of the PID controller is basically the difference of pk by pk minus pk minus 1. So what essentially would happen, this guy would go away, of course, and the second would be the key aspect comes in the integral term and the derivative term. So integral term you see ek, so you have integrated, so in the first, so here in the first case you have integrated till k and you are minusing the integration till k minus 1. So your integral term will only contain one term which is ek. Why? The derivative term would contain multiple terms. It is ek minus ek minus 1 minus ek minus 1, of course, minus minus plus ek minus 2. So ek minus 2, ek minus 1 plus ek minus 2. This is the velocity form of the controller. You can choose one of this. And there are certain advantages of velocity form over the position form. Why? Because the integral term has gone away. It's not there. And integral term is the main consequence of, rather not the consequence, the reason for integral wind up. Integral wind up, because there is no integral term here, so there is no integral wind up, but it contains implicitly the integral action between two successive steps. And also the most importantly, so you have to see here. So the left hand side is pk by minus pk minus 1, which is the delta pk. Your output is basically delta pk. So what we mean by that? So let's say your controller is updated at the 4th instant and you need the 5th instant. You are not recomputing anything on the 5th instant, but you are just adding a delta pk here. So pk at 4. So P4 at pk4, delta pk4 give you at pk, p at 5, and p6 would be p5 plus delta p5. So what are we doing here? So so this essentially means that you are basically utilizing your previous calculation. So some level of memory saving, because you already computed, so there is no point in recomputing anything. You just, so it's like, so these kind of algorithms are called recursive in nature. So basically it takes rather reduces the load of the overall computation, because you have already computed something and next is just an addition. So why it is good? So let's say you are working again. So you have to look at the customer of the controller, which is the control valve. Okay. For the control valve, so this P6 is coming in here and already your stem position is at P5. Okay. So let's say this is the stem position at P5. And delta P5 is just saying you just reduce this. So it gives you more continuous more continuous feeling of operation. While when you compute P5 and P6 independently and send into control valve, P6 is done. Okay, and P5 you have to, so P5 is implemented and P6 is like a discrete instant. So everything, so let's say if it is a ramp, big change, the load on the control valve would be more eventually, because these are all discrete instances. Now, while other is a small addition on the existing one. So it is this, here the transition is smooth. While if it is position, it may be little bit of what you call hard transition. Okay, so this is what I wanted to cover. Any questions on this?
No, sir.
Good. So now we would move into the overall control system design. So which essentially means that you are going to use all your skills in terms of aggregating things together. So let's go back and look at an example. Okay, so before it downloads, so let's kind of list down the overall components in the control system. Okay, so let's look at from a simple example. So there is two things coming in and finally one thing goes out, and assume that it's a missing problem. Okay, and here you have put an analyzer transmitter, and the analyzer transmitter is going to some controller, analyzer controller maybe, and you would give your set point here, and you might have your I to P here. Maybe let me erase this little bit so that just put this in a slightly. Okay, this is your I to P. I to P would be going to what? You have your control valve here, the control valve, and I to P. So of course, instrument air would be there. I to P might be communicating here, and this is possibly, I would say, this is some X1, W1, where W1 stands for the flow rate, X1 is composition, W2, X2, the 2 second stream and its composition, and finally some WX. W is the final composition and final flow rate. So what are we trying to do is you have to maintain X objective, maintain X at X set point, fine, by manipulating W2. Because your control valve is right here, here you don't have anything. So this is technically the disturbance line, because there is no, you don't have any control, right? Because this could technically disturb. So this is the manipulated line, and I think that's all about it. Okay, so when you write the over, so see there, so when you write the model, the final output transfer function, okay, X of S, fine, this would be like two components. One is your it's, so see, because there are two components, right? So one would be with respect to X1 and its transfer function. So let me just forget that. Because there are two input to the system, let me call it as X1 times G1. Let G1 be the transfer function that relates W1 X to W1 X1 to X plus X2 times G2. G2 is what? Your the transfer function, that, so maybe this is the G1 line, and so let me put it as 1 and this is 2. G is the model that we are going to model that you have made, that connecting input to output. So you have two components, one corresponding to the manipulated line and one corresponding to the disturbance. So this is one advantage that we have learned while developing the transfer function. You can write the linearity. So the superposition, no? So you can superpose x1 as a function and also x2 as a function to get your x up. So everywhere there is x, no? So s. So I am just removing it for simplicity. So first of all, this whole process. So this is the one component is your process model itself. Okay, so the second component, let's look back and look at here. One is your analyzer, transmitter, which is the sensor. The sensor should have a model because this is another device. See, everything is another, so nothing is uniform here. So this is your process done. Analyzer, transmitter is another device. Controller is another device. I2P is another device. Control valve is another device. So let's list down all of this. Process model, analyzer, transmitter, controller, okay, I2P, current to pressure transducer or current to pressure transformer, whatever you would like to call. Then your control valve, which is final control element, actuator, whatever. Okay. The process model contains your two components, your disturbance line, which is this, and the where you have kept your manipulated variable, which is this. So disturbance plus manipulated. So now how you play with everything together. Why this is very important is because, so see, you are adding a lot of external things into the system. So your process is inherently unstable because you don't have control over x1 or x2. Let's say you have not put any of this, okay? Any of the control system or any of these things, you have not, nothing you have integrated into the system. So now to control whatever the overall composition X, you have added various components to it. You added a sensor, you added a controller, you added a what you call current to pressure transducer, you also added a control valve. So these are all external elements. So see, except this guy, they are all externally added. Okay, for what? To control. So the external, and this resulted in your overall control system. So this is what you are going to do, implement it in the real plan. So it is very, very important for you to check that this added components are not making the system destabilized, because your original process model itself, process, you can call process model or process plan, whatever maybe, that itself is not giving you good result, and you are expecting when you add a controller, you would help it, but you cannot put control alone. You need to have a control valve, you need to have an actuator, you need to have a ITP converter, you need to have a sensor. They are all externally added along with the controller on the plant. Whether this overall, so element 1 to 5, specifically, you have to be very careful. Element that you have externally added, which is 2 to 5, will make your system destabilize or what? Because otherwise, what are we doing it? So you have added various components, and that itself kind of topples the entire business. So this is why we'll have to analyze the entire what you call process control system as a group, as a single entity, and decipher the inference. So maybe I hope my document might have opened now. Let me see. Yeah. Did I miss anything? Let me check. I have looked at transmitter. Okay, just give me transmitter we have seen, controller we have seen, ITP we have seen, control bar. Okay, everything has been counted. So I am just leaving the initial part of it. The process model development you already know. How do you do it? You write the mass balance, linearize, take the Laplace, and you will get two components, as I rightly told, one corresponding to W2, one corresponding to. So here is where we do control, because this is the manipulated line, W2, right? So this is X2, W2. Okay, and here is what the disturbance comes in. I think so. This guy is corresponding to the disturbance because you don't have any control, assuming no variability in W1. So you have two things: the flow rate and its composition. So you assume that the flow rate is somehow constant, but it's X1, the composition of that flow, that a particular component in the flow rate is varying with respect to time. Okay, so now let's look at each of these components. So analyzer. So analyzer, what it does, it takes the original variable and converts into milliamps. So any analyzer. So what is an analyzer? It is the sensor. So sensor takes inputs, physical inputs, okay, converts into electrical. So oftentimes the sensor, okay, so and so what are we doing? So this is like a transformation from one to two, and let's say the composition is maybe I don't know 2 gram per liter. It would gives rise to corresponding signal. Let's say it is 5 milliampere, and let's say it is 5 gram per liter. Okay, so it should correspondingly increase, and you might get maybe 8 milliamps whatsoever. So what are we trying to? So what do we say the analyzer or the sensor model means that? What is the output of the sensor for a given input of the physical variable? Because it takes the physical variable in and takes the signal uh, signal out. So there are various ways. So see, how do you get the sensor model? That's a big question. So when you buy a sensor, okay, oftentimes, so when you read, so they would give you an instruction sheet. They would most likely say how the dynamics of the sensor. So why there is a dynamics of the sensor involved? Okay, so that's a very important thing. See? So let's say it's like this, right? So let's say this is a heat water. So let's say this is a heating water bath. You put a thermometer here. So this is of course at 100 degrees here. This is thermometer. And what would you see as a function of time? This is time. So eventually the thermometer, if your thermometer is working fine, there is no problem. You would definitely get it would definitely show 100 degrees C. But you are inserting it from an ambient temperature. So let's say this is 28 degrees C, this is 0. Okay, so what you would most likely see is, so initially, and you put a stopwatch and started recording this thermometer measurement. This is what you would do possibly in the next lab coming next semester. Okay, so at the time 0, it is the ambient temperature. Maybe 1 second, 2 second, 3 second, maybe 4 second and 5 second. Maybe when you dipped it, it might first second it may temperature might rise to 40, then 60, 40, 60, maybe 80, and finally 100. Okay, so this is a very huge business. Whatever. So first second it reached 40, second 60, then 80, then finally 100, and it would remain there because the temperature of this bath is always 100. So what is that you are saying? So 0 time, so you would see something of this sort. So this is very, very similar to your first order response that you would see. First order system response, how it varies, it starts with something and finally it becomes steady. Oftentimes the sensors are therefore modeled as first order system with their time constant. So this TS means T sensor. Because finally it would reach the steady state. Because only problem is the delay. Eventually it would be reaching the steady state. So oftentimes the sensors are modeled first order system. Okay, so now what's the time? 11. Okay, good time. And so even my particular files got automatically closed. Just to add a few things. Okay, so we will stop here and next we will look at these particular components, how to model uh, uh, the things like control valve, I to P, and finally close the entire loop. Just a second, I'm sorry, and that I am taking more time, but I am just closing it down. In the so in the subsequent classes, really painful. Okay, so in the subsequent, so we have looked at here, subsequent classes we looked at the control system as well. So I will stop here and wish you a very, what you call, happy festival days and see you on next Wednesday.